So this is joint work with Wessam Sakla, who's with Lawrence Livermore National Laboratory. And this was work that I did over an internship at the Data Science Summer Institute at Lawrence Livermore this summer. All right, so today what I want to talk about is how to solve imaging inverse problems with deep learning inspired methods with very little data. All right, so before I actually go into our approach, what I first want to do is outline what exactly are imaging inverse problems and what makes them so challenging. So here are a couple of examples of imaging inverse problems, and here's the main idea. All right? So we essentially want to recover a clean image, x naught, from some corrupted version of it, which I call phi of x naught. All right? So x naught is our image, and phi of x naught are our measurements. So some common examples that we see in image processing are denoising, in-painting, and super resolution, where you want to recover an image from a noisy version, a masked version, or a low resolution version. All right, so these types of problems arise in a lot of scientific domains. So for example, in compressed sensing, you want to recover an image from its low-dimensional linear projection. And in phase retrieval, it's actually the nonlinear version of that problem. But one of the central challenges that arises in all of these problems is that there's an ill-posedness to them, meaning that there are a large number of images that are actually consistent with the measurements that we have. So we're in some sense trying to find a needle in the haystack. And so in order to actually find this needle in a haystack, what we need to do is have a model for what actually makes an image natural, or what makes an image actually fit the type of thing that we're looking for. All right, so what I'm going to do today is talk about what are some common deep learning image models for inverse problems, and these are going to be broken down into two categories. The generative models like GANs that you see that require a large amount of data, and some recent work that shows that randomly initialized convolutional nets actually can be good image models too, so they require no data. Right? So after I go through that, then I'll talk about what our recent approach is how to use a small amount of data to solve these problems, and how our approach compares with untrained networks, and how it's on par with generative models with far less data. All right? So I'll first go over into what are these high data regimes. So these are these generative models known as GANs or VAEs. All right? So these generative models are neural networks that are trained to create samples from distributions of images. So they've been able to create really realistic yet synthetic examples of things like celebrity faces and bedrooms. And they've been able to even create things like synthetic MRI scans, cells, and even human fingerprints. All right, so once you have a generative model that can create these types of images, how do we actually use them in an inverse problem? All right, so what you can do is use them as a generative prior, meaning that I'm going to say my image should come out from this generative model. How can I use that to solve my inverse problem? All right, so in order to do that, what you first need to do is actually train a generative model to output the particular signal class that you're interested in. So if you're doing an MRI imaging, you need to train a generative model to output a bunch of MRI images. And then now once you have that generative model, then you can directly optimize over its range to find an image that's most consistent with your measurements, right? So this optimization problem that you see on the bottom here, what that's basically saying is find an input to your generative model that'll give me an image that is most consistent with the measurements that I have. All right, so this sort of formulation has actually worked really well in problems like compressed sensing and phase retrieval, but one of the drawbacks to this is you need a ton of data to train these generative models. Right? So to create a good generative model for celebrity faces, you need at least 100,000 examples just to create a high quality generative model. Right? So what I'll talk about now are some recent approaches where people have actually used just randomly initialized neural networks to actually be good image models. All right, so I'll show you a recent experiment that kind of showcases this interesting phenomenon. All right? And so here what this experiment is showing is we have a noisy image, and we're going to try to denoise it by fitting a convolutional neural network to it. All right, so we're going to randomly initialize its weights, and then we're going to try to solve this optimization problem here on the left. All right, so we're just going to solve this via gradient descent, which is basically just saying find the weights of the neural network that best fit to your image. So notice we're trying to fit to this actual noisy image. And so here are the results here on the right. So both the red and blue curve are actually for two different architectures, but the phenomenon is the same. So you can notice that as you start the optimization process, the network actually fits to the clean image first, and then if you let it run for long enough, because these models are so over-parameterized, it's able to eventually fit to the noise. Right? But what you see here is that after only a small number of iterations, these networks have this bias towards actually a clean, natural image. So you can actually denoise images with this way via early stopping. Right? So based on these kind of two different approaches, having a generative model for your image prior or having these convolutional neural networks that are randomly initialized, what I want to do is kind of interpolate between these no to high data regimes. Right? So what I'm interested in trying to do is basically I want to create a new model that performs just as well as untrained neural networks with no data whatsoever. And then as you feed it even a small amount of data, its recovery success starts to improve. Right? And then hopefully over time, as you increase the amount of data, maybe it gets just as good of a GAN, but we'll see what ends up happening. All right, so here's kind of the general framework for the problem that we're going to be trying to solve. All right, so we're going to assume that we're given some linear measurements of an image. All right, so we just have our image x0, and we applied some matrix A to that image. So we're given these linear measurements, and then we're also going to assume that we're given some small number of examples of images that are drawn from the same distribution as the image we're trying to find. So here, we're calling these small number of examples low shots. All right, so we're given S low shots, and here, when you think of small number of examples, you can think of like 5 to 25 images. All right? So given these linear measurements and given these small numbers of images, then we want to find the true image that we're looking for. All right, so how can we actually try to do this? And so our approach that we propose is to try to actually pre-train a neural network with these few numbers of examples. All right, so what we propose to do is to solve this optimization problem that you see on top for some loss function. All right, what this is basically saying is to try to jointly fit an input space and the weights to fit to each of these few examples that you're given. So each of the examples are going to get their own latent code, and you're trying to essentially organize input space and find these weights to find this nonlinear mapping between the input space and some part of the data distribution. All right? And so in the case when the loss is just the L2 loss, this is actually known as generative latent optimization. And so what we're going to do is look at what happens when L is the L2 loss and also when L is something a bit more sophisticated like the maximum mean discrepancy loss. And we'll compare the two at the end of the presentation. All right, so what we want to first do is pre-train our network with these low shots. So we'll learn some information about the data distribution. And so once we've done that, how do we solve the inverse problem? So what we first propose to do is do it via a two-step process. So this is called this image adaptivity scheme. Right? So this is recent work by Hussein et al. That showed this worked pretty well for GANs. So what we're going to do is now we have our pre-trained model. So we're first going to try to find the best latent representation with the weights we already found. Right? So we're basically trying to solve this optimization problem here. We're trying to find the best latent code that gives us an output that's most consistent with the measurements that we have. So we're searching over input space to find an image that's hopefully within the data distribution. And so we've learned maybe a little bit of information about it from the pre-training, but not that much, right? Because we only really have a small number of examples. So hopefully this will give us a good initial solution. And then once we have this kind of warm start to our process, then we'll try to extend the range of our model by now optimizing both over the inputs and the weights at the same time. All right, so now using the solution that we found before, then we're going to optimize this objective function here using both the inputs and the weights. So the idea here is that the range of our generative model is extended, right? And we can basically search over inputs and weights to hopefully find a good representation of our image. So there's really a two-step process to this. First, we optimize over the input, then we optimize over the input and the weights. All right, so let's go ahead and see how this compares to some other types of models. All right, so here's a PSNR comparison for the compressed sensing problem. All right, so here, let me explain what these figures are. So on the left are the comparisons for models trained with a maximum mean discrepancy, and on the right is for models trained with an L2 loss. And so on the x-axis, you have what's known as the compression ratio. So this is the number of measurements divided by number of pixels. So the smaller compression ratio means that it's a more difficult problem. So things on the left are more difficult, things on the right are easier. Right? And then on the y-axis is the average PSNR taken over 50 different images. So the higher PSNR, the better. And so the curves I want you to kind of focus on are this dashed black curve. So that's a fully trained generative model for celebrity images. So that's trained on over 200,000 images, and that's only optimizing the input. And then the black curve is optimizing both the input and the weights of that model. All right, so that's a fully trained GAN. And then so the red curve is an untrained network. So notice it doesn't do too well for a low compression ratio and eventually starts to do better in a easier case. But notice here, as we start to increase the number of examples that we feed our model, our performance starts to get better. And then when we only use 100 examples, our performance in that green curve is fairly on par with actual generative models that are trained with over 200,000 examples. All right? And so we see similar phenomena for both MMD and L2, but the MMD seems to be more consistent in terms of the actual increase in performance that we see. All right? And so this is for the compressed sensing problem, where that matrix A has random Gaussian entries. And then so we also looked at what happens if you do another problem that requires some information about the data, like colorization. All right? So here's some examples of colorization experiments. So on the top row are the true images you want to find. In the second row are the grayscale measurements that we get. And so in the third and fourth row, these are results from a fully trained generative model. And so you notice that they get pretty good results in terms of being able to get the correct colors and things like that. And so notice in the fifth row, that's an untrained network, right? So it has no idea about what skin tones a face could really have, so it doesn't really know where to put the color. So it just completely fails at this task. And then in the bottom row is our model only trained with 10 examples. So with only 10 examples, our results are actually quite on par with these GANs that are trained with over 200,000 examples. All right, so even just 10 examples can really get you a really big increase in performance from no examples to 10. All right, so these are just two kind of results that we've seen in both two different types of problems, compressed sensing and colorization. And so just to recap what exactly our contributions were, so we proposed a scheme to try to solve imaging inverse problems with only a little bit of data by pre-training a network with these few examples. And we showed that our results actually increased with the amount of available data that increased, and we improved upon untrained networks and were somewhat on par with generative models with far less data. Thank you.